Hi guys, Mrs. Brummel here. This video is for 1.1. So we're in our very first chapter for AP Calc titled Limits and Continuity. So hopefully you've had a chance to just kind of read about what is calculus and look into kind of this infamous tangent line problem. There's a section in your book that goes about this. This is hyperlinked to on Google Classroom that takes you to that first video on AP Classroom that kind of describes what this tangent line problem is. So I'm just going to briefly touch on it, but the video is really great. So is the passage in your book. So make sure you check those out. Okay, so basically one of these, there's two main problems that summarize calculus, and one of these is this tangent line problem. So basically we want to find the slope of a line tangent to our graph. So we have this function f of x, and we want to find the slope of this tangent line. Now, in order to find slope, you guys know this from previous math courses, you need 2 points. Well, a tangent line is only a single point. So basically, I can create a secant line, which means it's touching our graph at 2 places instead of just 1. And I could calculate the slope that way, but it's not exactly the same as the slope of the tangent line. So, and I can gradually move those 2 points closer and closer and closer to this point C, C being the tangent point of tangency, I should say. And so basically I'm getting as close as I possibly can, but I still need those 2 points to calculate the slope. So we are going to use something called a limit. So a limit is that process of approaching a value and what is the resulting value that we see. So basically the limit, this is our slope formula, where I have f of x minus f of c, x minus c, but I don't want this to be c because otherwise I'm dividing by 0. So I want this c to be as close as I can get to c, approaching c, closer and closer and closer. And so we call that limiting. And so as I approach an x value that I want, without actually getting to that exact value, as I approach it, what is the resulting value that I see? Okay, so here's the notation. You guys are going to see this a ton in this first chapter. How I read this is read the limit as x approaches c of f of x equals L. I'm going to write that down here, how you would say that in words. So the limit as x approaches, that's what that arrow means, c of f of x is L. So that's how you say that in words. So here's kind of our formal definition. This is right from your book. The value of f of x can be made as close as we please to L, L being the limit value, for x sufficiently close to c but not equal to c. Again, I don't want x to equal c because then I get division by 0, but we want it to be as close as we can get to c to try and look at that exact slope at that point. And why we're interested in that slope, remember, it represents change, average rate of change. So we want to know about instantaneous change in calculus. We want to know about change at that specific point, not necessarily between 2 points that are far away. Okay, so for this first part, we're just going to practice writing this in words, practice saying it, and then we're going to interpret what it means. Okay, so I could say this as the limit, this in quotes like I'm saying it, okay? The limit as x approaches 2 of, and our function in this case is 5x, is 10. Okay, so what that means is as our x values get closer and closer to 2, the value of 5x gets closer and closer to 10. Okay? Okay, so some of you might be saying, well, what if I just put in 2 for x? I would get 10. So that kind of makes sense. We are going to actually use that quite a bit, but there's something really important for you to know that does not always work. So we're going to look at a couple examples here. Okay, and I'm going to zoom in just a little bit. Okay, these again are pictures from your book. So these are some different examples of limits. So here's our C value. So we can approach it from the left and from the right. So we're getting closer and closer and closer both sides. We're asking, as the X value gets close to C, what Y value is it getting close to? So that's what L represents up here. So sometimes that point is actually on our graph. Sometimes it's not. So in this one, the limit of this function is still L, even though there's no point exactly at L, it's approaching L. So even though there's a hole there, the limit of this one is still this value, okay? Same thing here, and even though this point up here is defined, this is not the limit value. This is the limit value, that value that it's approaching, same thing here. So a lot of times this is how it looks, but not always. So we wanna make sure we're aware of that. Some more important things to know about limits. So in this first one kind of ties into those graphs. The limit of L of a function as x approaches c does not depend on the value of c. So here my limit is L, here my limit is L, here my limit is L, even though f of c is not defined for those two graphs, or this graph, I should say. A function cannot have more than one limit, so it will only ever have one limit. If there's no single number that f approaches as x gets close to c, we say the limit does not exist, and we use this abbreviation DNE. Those of you that are Mean Girls fans, it is coming into play finally for you in a math class. The limit does not exist. Okay, we are going to move on. I kind of addressed this actually a little bit, but this is more formal. We can approach c, that x value, from two sides. We can approach it from the left and the right. So this is how we can denote that. So if I have x approaching a number with the little negative superscript, that means that's my left-handed limit. Okay, I'm approaching numbers from the left side, which means they're numbers that are less than c. A right-hand limit is numbers that are greater than c, and it's denoted with the superscript plus sign, and that is our right-hand limit. This is also something you can use. The limit of a function exists if and only if both of these one-sided limits are equal, okay? And we're going to see some examples here. Okay, so I'm going to use a table to actually help investigate a limit. So it says investigate this limit here using a table of values. So I'm actually going to switch gears, you guys. I'm going to open up Desmos. Okay, and I'm going to type these in. So I have the function e to the x minus 1. Oh, and let's put that maybe in parentheses so I can write it as a fraction over x. Okay, so I'm going to plug different values in for x. So in our table, I'm going to start from the left. So I've got negative 0.01, and that's also going here, negative 0.01. Oh, I forgot my negative up there. Okay, there we go. Okay, so you can see right here, this is what that equals approximately. So I'm going to write that in my table. So when I plugged in negative 0.01 for both those x's, I got sorry, I got to switch back again, 0.995. And the reason why Desmos is kind of nice, so now I'm going to put in the next x value. So all it did is add a 0 in each of those. So now I have an extra 9, 0.9995. Okay, one more 0 in here. 0, 0, 4 9s. 1, 2, 3, 4, 5. Okay, and then one more 0 for this last one. 5 9s. 1, 2, 3, 4, 5. Okay, so here's what I have in this table. Okay. So these numbers, so my x values are getting closer and closer to 0 from the left. So these are numbers less than 0, but they're really, really close to 0, and they're getting very, very close to 0. So that's accounting for this, right? Approaching from the left. So this is approaching from the left. These values are approaching from the right. So I'm going to start with the furthest one away. Same thing, I'm going to use Desmos to help me out. So I'm going to get rid of the negative and get rid of a couple zeros. Okay, so there's our first one. So it's 1.005. Okay, and as I move closer to 0 from the right side, okay, I'm writing these on my table and then I'll switch here. And okay, so here's my table. Okay, so these numbers, these x values are getting closer and closer to 0, but they're starting with numbers that are greater than 0, right? So these ones are approaching 0 from the left, these ones are approaching from the right. So they're approaching 0, okay? Now I look at the y value. So what did my function approach as the x's got closer and closer to 0? Well, from the left side, it looks like I'm getting closer and closer to 1. And from the right side, I'm getting closer and closer to 1. So as long as they're going towards the same value, the left and the right, that is our limit. If they were going towards different numbers, we would say the limit does not exist. So they have to approach the same number from the left and from the right for the limit to exist. So we would write the limit as x approaches 0 of e to the x minus 1 over x is 1. So I'm going to use the arrows here. Now that doesn't necessarily mean that when I plug in 0, I get 1, right? Because if I were to plug in 0 here, I'd get division by 0, which is not defined, right? But they approach 1. So it doesn't mean that f of x equals 1. It just means those y values get closer to 1 as x gets closer to 0. Okay, we can also look at limits from a graph. So we used a table in that one. We're going to use a graph here. So here, it wants us to look at, so here's my f of x, my function. So it's this line with a hole, and then it's got this point as well. So f of x, we want to look at what's the limit as x approaches 2. So as I get closer and closer to 2, what are the y values approaching? So my y values are approaching this hole, which is a y value of 7. So even though f of 2 doesn't equal 7, it equals 10, my limit is 7. Okay? All right, this one, so I kind of have a break in my graph here. So when this happens, and I'm looking as x approaches 0. So because there's a break, I'm going to look at it kind of from the left and from the right here. So from the left side, my y values are approaching 0. So I'm going to write the limit as x approaches 0 from the left of f of x is 0, right? My y values are getting closer and closer to 0. Doesn't it hit 0 exactly because there's a hole there? That's okay. Now the right-handed limit, so as I approach 0 from the right, so the limit as x approaches 0 from the right of f of x, those y values are approaching 1, right? That whole time they're 1. So these are not equal to each other. So if the left hand and the right hand limit aren't approaching the same y value, then we say the limit does not exist. Also, do not put equals does not exist because that doesn't make sense. So next to a limit, this is important on your AP exam. They're really picky about notation and things like that. So we do not want to put an equals here. We're just going to use DNE, and this is an acceptable abbreviation on the AP exam. Okay, so in class, you guys are going to use Desmos to kind of do these 3 parts. So you're going to plug in those values. There's kind of 3 parts. So there's 3 functions, 1, 2, and 3, and you're going to do these 3 parts for it. So you are going to use your graphing calculator to complete each table, determine the limit. So as, in this case, my x's are approaching 2 from the left and from the right, what is the y value approaching? Or if it's approaching 2 different numbers, the limit does not exist. And then on the next page, you're going to graph those. So you're kind of using the table and the graph to determine those limits. Okay, so I'm not going to go through those together. You guys are going to do that in class. I'm going to jump to these last couple additional examples. Okay, example 3. So this one, the table is filled out for us. Here's our function. Okay, so I have sine of pi over x squared. Okay. So, and we're trying to evaluate the limit as x approaches 0. So here's some values. They left it in fraction form. That's fine. Okay, but notice I am getting closer and closer to 0 from the left, closer to the right, and look, it's 0, so I would say f of x approaches 0. So based on this limit, I would suggest that the limit is 0, right? As my x values get closer to 0, my y values are also 0. Now, this table was created for the same function, okay, as x approaches 0. So these numbers are still approaching 0, right? They're getting closer and closer to 0 from the left, closer and closer to 0 from the right. But look at, these are different y values. So in this one, you would say that the limit is 0.707, right? So those are not the same, even though we use the table to evaluate the same function. So it does matter what values you pick, and you might not necessarily know that because you might not know what values or what the function looks like. So something I would encourage you guys to do is to graph it every time, because then you can see. So basically, what does this tell you after looking at the tables is I would say the limit does not exist probably because we got two different values as we looked at x's approaching 0. Now, what does this tell you about tables is that tables alone are probably not reliable. Tables alone may not be enough to determine a limit. So as I mentioned, I would suggest graphing this as well. So I'm going to graph that function so you guys can see why the limit does not exist as well. So we have y equals sine of pi over x squared. So in this one, you guys can kind of see the graph already has formed over here. And if I start to zoom in, so basically it gets tighter and tighter and tighter, but what this is it's oscillating back and forth. So it's never approaching a single value. It's constantly bouncing back and forth, bouncing back and forth, bouncing back and forth. So that's why the limit does not exist. So using the graph with the table can be a really useful tool, okay? All right, now this one, we're gonna use our graphing calculator to investigate, okay? I'm actually gonna use my TI-84 on this one, okay? So if I were to graph this function, so we are gonna go to y equals, and I'm gonna type in this function. So I have 30 divided by 2 plus x squared. All right, and I just want, so sorry, this is your standard window. So your default on your calculator will have these values in your window. Go ahead and just graph it with that. So as I look at this, I'm trying to find the limit as x approaches 0. So I look at the left, I look at the right, and it looks like my graph is just shooting up. Like there's maybe a vertical asymptote here. So if it goes up forever and it's not approaching a single value, we can also say the limit does not exist here, or we can say it's approaching infinity. We're actually going to talk about that a little bit later. But be careful. What if my whole graph isn't showing in this window? In this case, that is actually what's happening. So it's really easy to say my limit as x approaches 0 of this function is infinity or does not exist, either one. But that's not actually true. And so because our window is set to a standard one, there's this cool option of zoom. And then we can go to zoom fit, which is option, oh, I went too far, option 0 for me. And then it's going to try and fit the majority of my graph. So I actually here can see that, hey, it crosses a value at 0. So that's the value that my graph is approaching. So another cool option here is I can hit zoom decimal. And actually, sorry, I'm going to go back to that zoom. Well, that's fine. Okay, so here's something else I can look at, you guys, is now that I'm in zoom decimal, I'm going to go back to my graph. To see that, if I hit this trace option, the zoom decimal goes up by 0.1. So it really increases at a small value, which is kind of nice when we're finding limits. So look at my y value as I approach 0, y is crossing at 15. And I can I'm going to get further and further away. So let's say I start at 1 and I get closer and closer to 0. My values look like they are approaching 15, right? Look at those last couple. There's my y value, 15.3, or excuse me, 14.3, 14.7, 14.9, 15. And then from the left side, -1, and as I get closer and closer to 0, 12, 13, okay, and I'm getting real close to 0 now, 14.3, 14.7, 14.9. So it does appear to be approaching 15. And again, that zoom fit, I can kind of check that out as well and see actually that Y value there. And looks like it is approaching 15. So that's where we want to make sure that we look at the whole graph and not just assume based on our given window. All right, guys, that's everything for this window. Thanks for watching this video.